Okay, once again I will continue with vertical stress distribution, and I have in the previous module lecture I have just given the what is Boussinesq theory. That means that was the theory developed initially when a point load applied on the ground surface. Then what is the stresses at different depths and different distance from the load point of application, and only one equation application I have shown, and by using that how to find out the significant depth etc. that or that pressure bulb is nothing but the line joining the equal pressure intensity, and that I have shown. Now in foundation engineering, when we apply this Boussinesq theory, there is a little dissimilarity. What way? We generally apply the load through a certain dimension, that means through footing or foundation, and which has a definite dimension. It can be circular, it can be rectangular, it can be square or any other shape, through which actually the foundation load or structural load through foundation soil will be transferred. But the theory of Boussinesq is given, that is basically for a point load. But this point load actually formula we can utilize also approximately to find out the stresses. Later on we will show you how to again integrate this point load for a area etc. But right now I will discuss how to use point load for the foundation load. Suppose the foundation dimension, suppose A by B, and applied a load intensity something Q, and then how I will apply the point load. Point load supposed to be Q only at a particular point, but foundation will have a dimension. So that is application I will show first, and subsequently I will do some other application. So this one let me I will consider suppose a square foundation. I will consider a square foundation like here, and I will show initially you can ignore these dots and also ignore those lines. You can consider this is the foundation. This is the foundation of suppose square foundation, and suppose the dimension is 3 meter by 3 meter, and suppose load is applied 100 kilonewton per meter square, that is kPa, and for this loading find out vertical stress at a depth suppose 2 meter below the center of the footing. So that means I want to find out vertically below the center of the footing. So that is my requirement. So that means since our Boussinesq formula is as shows like this, I apply load here and at a radial distance, and this is R and this is Z, and this point we find out the stress. But now if radial distance becomes 0, still I can use this equation, R can be 0. In that case also always throughout the below the depth of the loading I can find out the stress by using this equation. So that is what. So this is the requirement. That means I have to find out below the center of this footing, and now you can see this is the equation we have shown before, 3q by 2 pi z square 1 by 1 plus r square by z square 5 by 2 to the power 5 by 2. Now if I want to find out the point load formula, and by this using this equation, then what I can do, though all those in this footing the pressure intensity Q is 100 kPa acting, this is a pressure Q, that small q, whereas capital Q we can imagine as Q into area, Q into area. So Q into area if I do, then it will be ultimately 3 into 3 9 meter square is the area, and 100 is the intensity. So, 900, ultimately Q become 900 kilonewton. Now, this with this 900 kilonewton load, that I can assume as Q, and Z, suppose as it is mentioned that 2 meter below the foundation, and another thing is mentioned that I have to find out 2 meter just vertically below the center of the footing. Center of the footing means here, and if I imagine the entire 900 kilonewton load is acting through this center, and then if I put r equal to 0, then r by z become 0, r by z become 0, and then 1 plus r by z, 1 plus 0 to the 5, so this become ultimately 1. So, ultimate equation left here 3q by 2 pi z square. So, here I have used this one. This after doing this, the total load on the footing is 900 kilonewton, considering a point load acting on the center of the footing and substituting z equal to 2 meter, r equal to 0. What is the logic for r equal to 0? I am considering load is acting here, and also simultaneously load is acting here, and simultaneously I am considering that stress also below that point. So, that means I am not going away from the load point. So, r becomes 0. So, if I put this thing, then ultimately your sigma z become 3q by 2 pi z square. This is the equation, and if I put all those values, the value comes 107.43 kilonewton per meter square or kPa, whatever there. So, this was initially you have applied on the surface 100, but at 2 meter below, if I consider as a point load, then it is more than that. So, definitely this is a very approximate one, but if I do little modification to it while applying this point load application or point load formula, you may get quite accurate results. That is what I will try to see or show you in the next slide. That is you can see this, though I have I could apply the point load formula to a footing of 3 meter by 3 meter size loaded with 100 kPa pressure, and at 2 meter depth I could find out some value, but how accurate this value we do not know, and I could see that we have applied the pressure of 100 kilonewton per meter square at surface, but at 2 meter depth the value become little more. There is a doubtful whether it is true or not. Now, we can do a minor modification. Suppose the entire foundation area can be divided into a number of small units, and Boussinesq formula can be applied on the small unit, and finally, cumulative effect of all parts at any desired location can be obtained by summing them. So, that means what? If I have a footing like this, I can make a number of small unit, and I can consider one load is acting here. I can find out effect of this load at this point. Okay. So, like this, I have applied load here, suppose, and I want to find out the effect here, or little clearly let me do. Suppose I have divided like this, and I want to find out effect of this part, suppose here. So, this become r, this area into this q will be the capital Q, and z, whatever z will be given, that z can be used. So, and then like this, if I want to find out effect of this to this, I can find out, because between this distance between this to be taken as another r, I can find out effect of this to this, then this distance between this can be considered another r. So, like that I can consider effect of this to this, then another, I can consider effect of this at this point. Like that I can find out distance of the desired point from the point of application of the load, and then I can apply the Boussinesq formula again and again, and then finally sum it, then to get the stress because of the entire loading area. So, that is the thing we will try to show here. You can see smaller the unit size, better is the accuracy. That means, if I make very small my mesh, then I will get more accurate, but sometime for practical work you need not do. You can do a few division, that will be enough, that I will show you by some calculation in the subsequent slide. The same problem can be solved by dividing the foundation area into 4 small parts and 9 small parts, and its effect on the final result can be seen. That means, whatever foundation I have taken 3 meter by 3 meter, and I will now divide into 4 parts once, and then again I will divide by 9 parts again, and I will see how is the results. First, let me see divided by the 4 parts. So, this is the one initial first page I have shown with dotted lines. So, these dots are now essential. So, these are the dots now, and I have divided the 3 meter by 3 meter footings in 4 parts. That means, each part will become, this will be 1.5, this will be 1.5. So, that means, each part will become size become 1.5 meter by 1.5 meter, and this 1.5 meter by 1.5 meter area, the load will be actually loading will be 100 into 1.5 into 1.5, that means 2.25 kilonewton, and since I have divided into 4 parts, obviously the load acting on this part will be 1/4 of that. That means 900 was total, so it will be 2.25 kilonewton. Or it is not 2.25, 225. It was 900, so it will be 225. So, now Q1, Q2, Q3, Q4. Suppose if I consider this is 1 and this is 2 and this is 3 and this is 4. Everywhere, if I consider this is a Q1, this is Q2, this is Q3 and this is Q4. Then Q1, Q2, Q3, Q4 all are equal, and all are equal to 225 kilonewton. At the same depth 2 meter, depth is kept same, and center of the foundation, that means load is now applied here, and I want to find out the stress at this point. Load is applied here, stress to be found. So, similarly load is applied here, stress is here, and so now I can you can see that whatever distance from here to here, what same distance from here to here, same distance here to here, same distance here to here. So, that means I need to do only one calculation, and simply if I multiply by 4, then I will get the effect of the entire area. So, that is the thing. So, what is the R now? So, distance from the center to the center of the smaller footing is suppose R1 if I say for segment 1, R2 for segment 2, R3 for segment 3, like that if I proceed, and all will be R1 will be equal to R2 will be equal to R3 will be R4, and that will be equal to how much? So, this is actually the distance. So, so this under root, so this will be R will be equal to under root 1.5 by 2 whole square plus 1.5 by 2 whole square. So, this is the one, that means you have to find out this distance. So, this plus this square plus this square under root will be the R. So, that is the one, if you calculate, then you will get 1.06. So, now I have to apply for, suppose I am considering for this part 1 to this point. So, that I say the del P1, then 3 Q1 by 2 pi z square, 1 by 1 plus R square by z square 5 by 2. So, this is 3 into not 2.25, it is 225 and 2 pi z square, and 1 plus 1.6 square by 2 square to the power 2.5, then you will get around 14.46 kilonewton per meter square. So, this is the value we are getting for 1. So, if I want to find out this one, then it will be added, for this one to be added, for this one also to be added. So, finally, it will be, that means 4 times. So, delta P, that means because of the loading of the entire area at the center, whatever stress we are getting, I assume that as a delta P. Then delta P become 4 into delta P1. So, 4 into 14.6 is 57.85. So, this is the stress actually we are getting if I divide into 4 parts and apply the Boussinesq bond formula. Now, as I have mentioned before, that if I divide it into a number of more number of segments, you will get more or better results. So, now I will try to show you dividing it into suppose 9 divisions. So, if I do that, how it will be? So, this is the one, suppose it is a 9 divisions are made, and if 9 divisions are made, then you can see that this is suppose this one you can see now number of them we can number it. R2 become 1 meter. So, each becomes, since it was total 3 meter. So, these become 1 meter, these become 1 meter, these become 1 meter, and from here to here I now consider that center of each point load is applied. So, that means 9 concentrated load to be applied at 9 locations, and because of that total effect to be obtained at this point. So, first is 1 suppose, and suppose this is actually suppose 2. So, this is suppose 2 and this is suppose 3, I am numbering, and you can see it is a symmetric. This one is totally independent, only one, and this 2, this is also will be, this also will be 2, this also will be 2, this also will be 2. That means effect of this to this, effect of this to this will be equal. Similarly, effect of this to this also will be equal. Similarly, effect of this to this will be equal. So, that means I will consider R1 1, that is center one is the 1. I will take R2, that means this is the one just beside this one, that is R2, and I will consider another diagonally side, that is R3, and that is 1. So, we can calculate now. If I calculate R1 is obviously 0, when I applied center of this loading, then your radius become 0. And when I apply load here and find out the effect of here, what is the radial distance? You can see this is 1 meter and this is 1 meter. The half of this 0.5 meter, half of this, the distance between these will be 1 meter. So, R2 become 1 meter. What about R3? R3 will be this distance and this distance and under root of that. So, this distance become 1 meter, again this distance is 1 meter. So, ultimately your this distance R3 will become R3 actually under root 1 square plus 1 square. So, ultimately under root 2. So, that is what it is shown. So, 3 different R's are shown. So, R1, R2, R3, R1 is 0, R2 is 1 meter, R3 is root 2. Now, I can find out del P1. Del P1 will be equal to 3 Q1 by 2 pi z square 1 by 1 plus R1 by z square to the power 5 by 2, and R1 since 0. So, ultimately, and what about the Q1? The Q1 will be, since I have divided into 9 part. So, it will be 900 divided by 9. So, 100 kilonewton, each will be 100 kilonewton. So, I will apply 3 into 100 divided 2 pi into z square, then I will get delta P1. So, this is the value 11.936, and so that is the one. And now, I will find out another value, that is delta P2, that means effect of this to here. So, there actually if I do delta P2, if I write, will be 3 q2 by 2 pi z square 1 over 1 plus, here r is actually 2 and z also 2 to the power 5 by 2. And if I, so q1, q2, q3, ql all are same. So, it will be again 100, 300 by 2 pi z square, and this z actually nothing but 2. So, you will get, if I apply this equation, then I will get this value delta P 2. And then another this one delta P 3 will be equal to 3 q 3 by 2 pi 3 q by 2 pi z square 1 over 1 plus 2 root 2 square means 2 by 4, suppose 2 square is 4 divided by 2 5 by 2. So, this is the expression for delta P 3. So, this delta P 3 expression if I use, then I will get this value. So, now if I do this 3 calculation, then I need not repeat the other calculation that I have numbered. Suppose there are 1 2 3 4 6 5 6 7 8 9 division, but I need not calculate for all 9 divisions. So, I can now what I can do, I have shown already this all 4 are same effect on this. Similarly, this all 4 are having same effect on this. So, because of that I can find out finally del P equal to 4 times del P 1, that is only 1, and 4 times del P 2, 4 times del P 3, and then the value become 56.592. And you can see and compare that previously when I have divided into 4 parts only, I have got quite close 57 point something. I can show you again this one. This is actually 57.85, whereas we are getting here 56.59, that is quite close. And in fact, in civil engineering calculation we need not get more accurate, actually some more than that accuracy sometimes is not required, because always we are applying in a ton load and civil engineering most of the cases. So, sometime, so this much division, that means 4 division is quite good, 9 division also improvement is marginal. So, that much may be sufficient sometime. So, this is the application. So, if you want to, obviously when there is a accuracy is required, suppose you want to divide this one more number, suppose, then I can also divide still in bigger number of like this, any number of mesh I can do, and then I can number it, and from symmetry I can locate center, and from center distance I can find out del P 1, del P 2, del P 3, del P 5 like that, and then sum it up to get the total effect. So, but what I could show that maybe if it is square foundation 4 division is maybe good enough, or even 9 division is good enough, but when it is required, then we may go for more number of division. Now, another application I will show. This is a application where I am showing there is a 9 footings. Suppose there are 9 footings here, and suppose footing 1 2 3 4 5 6 7 8 9 are there, and here actually I have to find out suppose this is 1 2 3 4 5 6 7 8 9. So, these are the number of footings given. So, because of this loading, suppose we have to find out, you can see all 9 footings are loaded. You have to find out the pressure below the footing 1, 2 and 5. I will just show the application the below the footing 5. So, this one, and rest of the things you can try yourself. So, I will show the application of footing 5. So, for this you can see that footing size is 1.8 by 1.8, and center to center distance is 4 meter. So, with this, so what I can do, if I want to find out the pressure between below the footing 5, then I have to find out effect of this footing itself, then effect of this, 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 all around. Now, what I have shown in the previous one also, that this and this are same effect to this. So, I have to calculate only one, and similarly this or this and this 4 are also same effect on this. So, I will calculate. So, I will do 3 calculation, one for this footing 5 itself, another for footing 4, another for footing 3. If I do that, and you can see that calculation for below footing number 5 is shown here, as I have already mentioned, and pressure under footing will come from all 8 surrounding footings and the self, that means middle on footing, and because of symmetry 3 calculations are required, as I have told you. This is the one. Suppose the footing here, footing here, footing here. So, 9 footings are there, and you can see for center footing r equal to 0. So, that I am considering, suppose del p naught. Suppose this is del p naught because of the self at this point, because of this footing only. So, each footing load is applied. So, 270 intensity was 287 point something, sorry. Pressure intensity was 287 and size of the footing 1.108. So, it comes approximately 930 kilonewton, and with that I will do calculation. I am taking 930, and so this footing actually I am calling as 1, and this one I am calling as 2, and this is 1, and I am calling this as 0. So, in that case I will calculate distance to this to this distance will be 4, and this to distance will be 4 root 2. So, del p 1 actually 3 q by 2 pi z square at 3 meter depth, 1 by 1 plus 4 square by 3 square 2 to the power 5. So, it will be 3.836. Del p 2 means this one to this. So, this distance will be under root 4 square plus 4 square. So, that will be 5.66. So, 3 into 930 2 pi z square 1 plus 5.6 square by 3 square. So, to the power 2.5 it comes 1.11. You can see that effect of this footing will be more here than effect of footing of this two here. So, this is slightly far. So, effect is less. So, you have got less, and for this footing you have got effect more. So, these two you have got, and this footing itself, if I put r equal to 0, del p naught we are getting 49.338. Then what is the total delta, total pressure because of this all 9 footing at this because of the 9 footing loaded. I want to find out the pressure at this below this footing. Then what I have to do? I have to find out the pressure because of this footing only, applying center, and then 8 footings I have to apply. So, for that what I will do, delta p will be delta p naught plus 4 delta p 1 plus 4 delta p 2, because 1 2 3 4, similarly 1 2 3 4. So, this we have altered. So, you are getting 69.13. So, this value you have getting, and another thing is sometime middle footing which is 1.8 by 1.8, that actually sometime if you feel you can divide into 4 parts, then you will get better results obviously. Otherwise, approximately this is the result you are going to get. So, that means for 9 footing loaded you are getting the foot pressure below this, and similarly it is mentioned below the footing 1 and 2. That means I have to, if I consider below this footing, then I have to find out distance from this footing to all, that to be taken as r1, r2, r3, r4, and z is constant, and same formula we have to apply again and again, and then add it to get that. Similarly, I have to find, if I want to find out below this footing pressure, then I have to consider distance from this footing to all footings, and then R1, R2, R3 you designate, then calculate applying the same formula, then sum it up to get the full. So, other I have shown only one, that is middle footing, that is center footing. The other two edge footing, what will be the pressure, that you may calculate and practice. Okay. With this I am closing this one. Thank you.